Good morning, everybody. Today is May. No, it's not May. It's June. Today is Friday, and it's June 5th, 2020. And today we are going to wrap up our crash course on acids and bases. So if you would please access the Acids and Bases Guided Notes Part 2 that's up on Google Classroom. It looks like this. Let's see. There we go. This one, Acids and Bases Guided Notes 2. Okay, so we're going to work our way through this today. Let's see, we already did the guided notes number 1. We talked a little bit about titrations the other day. I asked you all to do the titration problems for homework. Hopefully you got to see the answer key. If you had any issues with that, you're welcome to ask me either now or at the end of class. You did the titration simulation the other day as well, or yesterday rather. And I know some of you had a little hiccup. I'll talk about that in a few minutes here. And then you read the Invisible Fire story. This is one of my favorite stories to read. I think it's pretty interesting. I hope you liked it too. You filled out the Google form. I'll give you guys some points for that. And then tonight, I'd like you to please work through this acids and bases calculations worksheet, and the answer key is there. It involves pH calculations, and I'm going to teach you how to do that today. So at this point, would you please open up this acids and bases part 2. We're going to work our way through that today. I don't mind if you just have it accessible on your computer and maybe you're taking notes off to the side, or maybe you chose to print it and you want to take notes directly on it. Totally up to you, whatever works best for your learning style. Just so we're all clear for the remainder of the school year, here's what you can expect. On Monday, I'm going to put a acids and bases quizam up for you, okay? So I know we've been moving pretty quickly over the last few weeks, but again, I'm just teaching you for exposure rather than for mastery at this point, so that next year, when we're in varsity chemistry and I bring up an acid as being a hydrogen donor, you go, oh yeah, I've heard that before. Okay, so I'm just trying to lay a foundation for varsity chemistry next year. Monday is going to be acids and bases quizam. And then on Tuesday, we're going to meet at about 10:20 in the morning is my meeting time with you. And I have a plan to, it's fun. Okay, I think you're going to like it. I have a group project for us to work on, but it's not really a project. It's more of a game. And you're going to get credit for being in class. So participation points for showing up Tuesday at 10:20 a.m. Okay, and let's see, I'll take attendance in class that day, and we'll have a little competition. It'll be a group competition, and you might even be able to earn some extra credit points if you win the group competition as well. And then a couple of you have chosen to do some explainer videos. We'll watch each other's explainer videos, and then we'll say our farewells, and that'll be the plan for Tuesday. I actually have a meeting with administration at 11:30 on Tuesday, so I don't anticipate Tuesday's class will take the entire time. I'll use you. I'll use your time up until about 11:30, and if we finish early, then great. But at 11:30, I'm gonna have to go. So just a heads up on that. Okay. So I'll plan on having the quizam up for you guys on Monday, and then I'll see you Tuesday at 10:20. Please be on time to class on Tuesday at 10:20, okay? All right, let's go ahead and get started today with our acids and bases notes part 2, where we get into some pH calculations, okay? So first bit here says, I'm gonna do my best to annotate directly on this. So, can I zoom in here? Sorry. Well, I guess that's not going to work. Wonder if I can try this. All makes it, there we go. Now I can zoom in and out a little bit. It's nicer. Okay, so first thing, this is just a warm up. Normally I would have you all do the warm up on your own, but we're in a different style of learning now. So let's go ahead and just do this together. First thing we come across here is, what is the name for the H3O plus ion? One disclaimer I have to make about this entire guided notes is that all of my superscripts of charges became subscripts for some weird reason. So this plus sign should really be a superscript, okay? So in acid-base chemistry, the first thing you need to understand about acid-base chemistry is that it always takes place in the presence of water, okay? There's always water present in any acid-base reaction. So your acid and base solutions are always going to be aqueous solutions. You can always assume that water is present. And so essentially what this H3O plus ion is water molecule plus an extra hydrogen, okay? And really acid-base chemistry has a lot to do with hydrogen ions, okay? So the name for this ion is called hydronium. It's kind of like water, right? Hydro, and then remember the IUM ending means positively charged. So it's kind of like water with an extra proton with a positive charge, okay? Now, I'm going to tell you that the hydronium, the H3O plus, is used interchangeably with a hydrogen ion in acid-base chemistry. So in other words, if you see H plus, and again, that plus should be a superscript. I just can't do it with my annotation here. But if you see H plus, that's just a hydrogen ion, right? Right, a hydrogen ion combined with water is hydronium. And since water is always present, these two things are used interchangeably. So just get used to it. Just know that if you see H3O plus, it means the same exact thing as a hydrogen ion. It's just plus or minus a water molecule, okay? And then the other thing that's a little tricky is it's also used interchangeably with the word proton, right? And you might think, well, why a proton and a hydrogen and a hydronium? How are those all the same thing? Let me grab my whiteboard and I'll show you. Okay, so if you think back to the very beginning of the school year when we learned about isotopes. Let's see if I can adjust this here so you can see. Okay, we learned that there's 3 different isotopes of hydrogen. They are protium, deuterium, and tritium, okay? And they differ by the number of neutrons, right? Well, that's my lighting here is not fantastic. I'm trying to get the glare off. Hopefully that's a little better to see. Okay, so 3 different isotopes of hydrogen, protium, deuterium, and tritium, okay? By far the most abundant type of hydrogen is protium. Okay, and protium is 1 proton because it's hydrogen. It has 0 neutrons in the nucleus, and then it has 1 electron on the outside, okay? Now, if it's that, and that's just hydrogen, that's the most common form of hydrogen. Now, if it becomes hydrogen ion with that +1 charge, that means that it lost an electron, right? So if it loses that electron, now really all it is just a proton with 0 neutrons. So hydrogen ion is used interchangeably with a proton. Okay, because really that's what a hydrogen ion is a proton. And then if I were to add water to this, then it basically becomes H3O plus. This is a polyatomic ion, right? Has multiple atoms that with a charge, and that we call hydronium. Okay, so just remember that in acid-base chemistry, if you see the word proton, hydrogen ion, or hydronium, all of them mean the same exact thing. Okay, they are all used interchangeably. I know it's a little confusing, but if you just accept it, then it makes our lives a whole lot easier. So again, I'm just gonna kind of highlight or underline this so you guys can understand what I mean here. Let's do this. So again, the words hydronium, which is just water with a positive charge because it gained an extra hydrogen, hydrogen ion, or proton, they all mean the same exact thing. Okay, they're used interchangeably. Okay, next, what do brackets represent? For example, if I put brackets around that hydronium ion, you guys should know this, it means constant. And usually concentration is measured in molarity, right, which is moles per liter. Be careful, there's some students in here who keep putting just a lowercase m as their abbreviation for moles. Moles is abbreviated MOL. I know it's not much of an abbreviation to just drop the ES, but the lowercase m means meters. Moles, if you want to abbreviate moles, is MOL. Okay. What is an aqueous solution? Hopefully you guys remember that aqueous means it's dissolved in water. In other words, water is the solvent. Okay, what does molarity measure? Molarity measures moles of solute per liter of solution. Weeks ago, okay. And then predicting the products of the neutralization reaction. So this is what we did the other day. Remember, acid plus base makes salt plus water. So the hydrogen comes from the acid and the OH comes from the base to make water. And then what remains is the salt, right? And I can do that for all of these. The hydrogen comes from the acid, the OH comes from the base, and then what remains is the salt, okay? Hydrogen from the acid, the OH from the base are going to get together, and then what remains is the salt. Okay, so here we're going to get H2O as a product, salt, plus this, I'm sorry, H2O is the water, and then the salt is going to be formed from potassium and nitrate. Potassium has a +1 charge, nitrate has a -1 charge, so crisscross applesauce, and we just get KN3. Okay, and that's my salt plus water. Here, and then it's already balanced that way too, just 1 to 1 to 1 to 1 ratio. Next one, we have calcium hydroxide and hydrochloric acid. We're going to make water. Hydrogen from the acid and the OH from the base make water. And then what remains is the salt. So it's going to be the calcium with a +2 and chlorine with a -1, crisscross applesauce, and we'll get CaCl. And so that's calcium chloride, which means I'm going to need a 2 here to balance it, and I'll also need to add a 2 in front of the hydrochloric acid to make it balanced. Okay. All right, and then lastly, acid plus base makes salt plus water again. So I think to balance this, I'm going to end up with 2 water molecules. And my salt is going to be magnesium and sulfate. Magnesium has a +2, sulfate has a -2. Crisscross applesauce and reduce that 2 to 2 ratio. It ends up being MgSO4. And I think it's balanced just like that. Okay, and so all of these salts, if you think back to solubility rules, they're all soluble salts. Remember, nitrates and alkali metals are always soluble. Calcium chloride, also soluble. Halogens are usually soluble. Magnesium sulfate is also going to be a soluble compound. Sulfates are generally soluble, except with castor bear, but it's not a castor bear. So anyway, all of these would be aqueous. So the H2O would have a little liquid next to it, and then all of the salts would be dissolved in water. They'd all be aqueous. Okay. Since I can't do subscripts, I'm not going to put the states of matter, but you could put states of matter in there. And then again, salts, the acids and bases are always aqueous as well. Okay, so all of these reactions are going to take place in the presence of water. So hopefully that was pretty good review for you. Let's move on. Okay, reviewing our naming. Okay, so we've already done nomenclature. We did it a while ago, but I just want to refresh your memory on naming acids. So remember that if the formula begins with hydrogen, it's an acid most of the time. If the acid contains no polyatomic ion, then it's what we call a binary acid, where it's just hydrogen and one other element. And you use the prefix hydro, and then the root name of the second element, and then ic acid, okay? see, write the prefix. I think that there's a mistake on here, actually, I just realized. Write the prefix hydro, then the root name of the second element with a, it shouldn't say IDE ending. Please replace that. I knew that there was a mistake somewhere here. It should say ick ending. Okay, it should be an ick ending. Okay, so with the ick ending and then acid. All right, we'll practice in just a moment. Sorry about that typo, I should have caught that. And then if the acid does have a polyatomic ion, we call it an oxyacid. If it ends in 8, the polyatomic ion ends in 8, you change the 8 to ick and add the word acid. It ends in ite, you change the ite to us and add the word acid, okay? And so, here we go, sorry, we got some latecomers here. So with the polyatomic ions, you do not include the prefix hydro, okay? You only use the prefix hydro if it's a binary acid, just hydrogen and one other element. Some exceptions, HCN is called hydrocyanic acid, that's an odd exception. And then acetic acid is an organic acid. And acetic acid is a kind of a funny one. I know that this one came up yesterday when you all were doing your titration simulation. And I'm going to take this off screen share for just a moment so that I can use my whiteboard and explain acetic acid, okay? So acetic acid is an organic acid. And I think a lot of you, when you were doing your titration involving the weak acid and a strong base, you were getting the wrong calculation value for acetic acid. In other words, when you were putting in your value for your molarity, it was telling you that you were wrong, okay? And here's the reason why. So with acetic acid is a weak acid, okay? And the structure of the molecule looks like this. So we've got a carbon bound to 3 hydrogens, and then a carbon double bound to an oxygen, and then another oxygen and another hydrogen here. So when we write this, usually we write it as acetic acid like that, where you can easily see this is the acetate ion with the hydrogen out front, or sometimes like this, CH3COOH, okay? And the reason why we would write it this way, usually I write it this way, usually we write it this way just because it gives us an idea of what the molecular structure looks like, right? Where the 3 hydrogens are attached to the carbon, and then the COOH is a functional group off of that. Okay, so I often write it this way, and usually with organic compounds, we do write CH3COOH. Like we write it kind of to give us an idea of what the structure looks like rather than just keeping all the carbons together and all the hydrogens together, okay? So just be aware that when we have organic molecules, they're often written this way rather than joining the similar elements together, just because you can understand what the structure of the molecule is by looking at that, okay? But here you'll notice that this hydrogen is off by itself, right? It's not combined with the other hydrogens because this hydrogen is considered the only acidic hydrogen, okay? So these 3 hydrogens are not acidic. So in just a moment, I'm going to teach you that one of the definitions of an acid, and the most common definition of an acid, is the fact that it's a hydrogen donor. And so essentially what that means is that this hydrogen is going to fall off of the molecule, okay? So it dissociates from the rest of the molecule. So that's considered the only acidic hydrogen. These 3 hydrogens are not considered acidic because they don't get donated. Now, if you look at the structure of this molecule, you should be able to see a difference between this hydrogen and these 3, right? If you look at the bonds, you guys know enough about chemistry now to do this. This bond here is a single bond where they're sharing electrons. But if you think back to Funkelbrich, our good friend Funkelbrich, remember that carbon and hydrogen have almost identical electronegativities, right? So in other words, this bond is a very non-polar bond. They're sharing electrons very evenly. These hydrogens are really happy, right? This bond, however, between oxygen and hydrogen is a polar bond, right? The oxygen is much, much more electronegative than this hydrogen is. And so in this single bond where they're sharing electrons, it's a single covalent bond between two nonmetals, right? The oxygen is pulling on those electrons more strongly, right? And so since the oxygen is hoarding the electrons, the hydrogen goes, psh, I'm out of here, oxygen. You suck at sharing, right? And so it falls off, and that's what makes it an acid. Okay, these hydrogens have no reason to leave because they're sharing really evenly. They're in great little relationships with carbon. But this hydrogen is in a relationship with a very greedy oxygen because it's so electronegative. And for that reason, it falls off, and that's what makes this an acid. So when you were doing your calculations yesterday and in any future calculations involving titrations with acetic acid, the XA value is equal to 1. In other words, this is what we call a monoprotic acid. Mono meaning one, protic referring to proton or hydrogen that can be donated in to make it an acid. And so that is probably where a lot of you are making your mistakes. A lot of students were making this X value 4. I've never seen an acid that can donate 4 hydrogens. Okay, I always see the X value is either 1, 2, or 3. Donating even 3 hydrogens is very, very rare. Usually it's 1 or 2. Okay, so my apologies. I did not make that clear to you before your simulation. Some of you emailed me, which is great. I love it when you email me when you have questions. Please continue to do that. And that's what I'm here for. But that's probably where some of you made your mistake on that titration simulation yesterday. Okay, let's go back to our notes here. We'll start jamming through these a little faster here. So just a review of acids. Okay, let's practice naming the acids. Normally I would let you guys work on this on your own, but I don't need some time in silence here, so we'll just do it together. Okay. So HF is the first one. This is a binary acid. There's no polyatomic ion, which means I'm going to use that prefix hydro. The root name of the second element, fluor. Don't forget that fluorine is spelled F-L-U-O-R. That's always tricky. And then the suffix ic. Okay. Next one. Here I have a polyatomic ion. And you spot the polyatomic ion, NO3. NO3 is nitrate, so I change the 8 to ic, and it becomes nitric, and then acid. There's no prefix hydro because there's a polyatomic ion present. You only use the prefix hydro if it's binary, just hydrogen and one other element. Excuse me. Okay, next one, H2SO4. Spot the polyatomic ion. There it is. Told you guys you need to know these polyatomic ions. H2SO4, that's sulfate. We changed the 8 to ic. You might want to call this sulfic acid, but it's a little bit of an exception. It's sulfuric acid. Next one, it's just binary, hydrogen and one other element. So we use the prefix hydro. The root name of the second element is iodine, so it's iodic acid, right? Next one is just hydrogen and bromine. So prefix hydro, root name brome, and then ic. Next one, I spot a polyatomic ion. There's my polyatomic ion, ClO4. What's the name of that? It's perchlorate. So perchlorate, you change the 8 to ic, and it becomes perchlor acid. You guys try the last two on your own while I get my child in on a Zoom session. You did pretty good here. Let's see. It is, sure, what is it? Let's see if they emailed me. Sometimes they email me the code. Nope. I don't know which one it is, if it's Miss Hannah's or Miss Karina's. Here, let's see. Oh, wait, here, oh, no. I don't know, we could try this. You can try either one of these IDs and passwords, Brian. See the ones at the top?
Okay.
Yeah. Try those.
Okay.
Okay. Sorry, students. Okay. Back over to Google Chrome. Let's do this. Oh no, all of them got erased. Oh well. Let's try the last two. Last one. This is spot the polyatomic ion here, NO2. That's nitrite. So we change the ite to us, and this becomes nitrous acid. And then last one, HCl, that's binary. So we're going to use that prefix hydro. And then the root name of the second element is chloric acid. Okay. Hydrochloric acid is actually your stomach acid. It's one of the strongest acids that we have, and it's in our belly. It helps to digest our food. Okay. Now I will tell you, let's quickly go through the strongest acids. Am I going to be able to list this here? I'll list them up here, okay? I'm going to make a list over here of the strong acids. You know what, actually, I'm going to do this on my whiteboard instead. Maybe you can write it in your margin, okay? But I told you I would tell you the 7 strong acids today, and I'll tell you strong acids and strong bases. And what you need to do is just memorize these 7 strong acids. There's no other way to do it, really, is just to memorize them. I have a quick little mnemonic or trick to help you memorize them, though. So here's what we're going to do. We're going to start with high. Okay. And then from iodine, if you look at a periodic table and you go with the 2 halogens right above iodine, they are bromine and chlorine. Okay. So high, and then 2 halogens right above iodine, bromine and chlorine. And then you put 2 subscripts of 3 and 2 subscripts of 4. Okay. And then you make this one a ClO, and this one is ClO. So is this going to be ClO? No. So I'm going to have to write something else in there. And then you give all the others enough hydrogens to make them neutral, right? These are all -1 charges, so 1 hydrogen with a +1 charge will neutralize it. This is a -1 charge, so 1 hydrogen with a +1 charge. This is -1 charge, so 1 hydrogen, -1 charge, 1 hydrogen to neutralize it. And then SO4 has a -2 charge, so I'm gonna need to make it H2SO4 to make it neutral. So once again, you start with high, 2 halogens above iodine, bromine and chlorine, 2 subscripts of 3, 2 subscripts of 4. You put a ClO in front of this one, is ClO in front of this one. So is this going to be ClO? No. So you put something else in there and then just give them enough hydrogens to make them all neutral. And so these are your 7 strong acids. Everything else is weak. So all you have to do is memorize the 7 strong. Everything else is weak, and then you just, if I ask you if it's strong or weak, then you just know, okay? Because you've already memorized it. So again, this is hydroiodic acid, right? This is hydrobromic acid. This is hydrochloric acid. Notice they all have a prefix hydro because they're just binary. They're just hydrogen and one other element. This one, this is nitrate, so it becomes nitric acid. And remember, nitric acid was that really especially nasty one I told you about. This is chlorate, so this becomes chloric acid. This is perchlorate, so it becomes perchloric acid. Right, and all these would be acid after them too. Acid. Okay. And then this one was our exception. Instead of sulfate becoming sulfic, it's sulfuric acid. Okay. And then now you know what the X values are, right? All of these have 1 hydrogen to donate. So my XA value would be 1 for each of these. This one has 2 hydrogens to donate. So my XA value would be 2. Now, the word we use in chemistry to describe that is that this would be called monoprotic. In other words, only one proton can be donated, monoprotic. So the X value is 1. 1 hydrogen can be donated. Here, this one is 2 hydrogens that can be donated, so we call that diprotic. Di, 2, protic referring to protons, and remember at the beginning I told you hydrogens and protons are used interchangeably, okay? So just memorize those 7 strong acids and you'll be in good shape. Okay, so let's go back to our notes here. Okay, I'm going to start moving through this a lot more quickly now. So defining an acid. All right, an acid, there's a few different definitions of an acid, but I'm going to keep it simple here. An acid is a substance that donates a proton. Okay, so it's a hydrogen donor. Okay, and how does one determine the strength of an acid? Well, you can use what's called, let's see, how do I tell you guys this so you don't quite know? It has to do with equilibrium. Well, you could look at pH or what's called a Ka value, and we'll get into this more in varsity chemistry. But essentially, the stronger an acid means the hydrogen falls off, hydrogen is donated. So in other words, acid strength is really asking us how likely is that hydrogen to come off. If that hydrogen falls off very readily, if it happens easily, then it's strong, okay? And if it doesn't happen very readily, then it's considered a weak acid. We're going to talk about that in a little bit more detail. But the stronger acid, the hydrogen is donated very readily. And what I want you to remember is that strong acids, strong electrolytes. Think back to what that word means, electrolytes. An electrolyte is something that conducts electricity. Okay, so in other words, strong acids will break up into ions and they can complete a circuit to make the light bulb light up. I think I did this demonstration for you guys at school. If you remember my apparatus where I could put different solutions in and make the light bulb light up, strong acids will indeed conduct electricity. Okay, so here's an example of a strong acid. Nitric acid was one of my strong acids, okay? And what we see here is that the nitric acid, if you kind of follow what's happening in this reaction here, the hydrogen is going from the acid to the water, okay? And it breaks up. Well, you can see the hydrogen and the nitrate break up here. And then the hydrogen and the water will get together and they form hydronium, H3O+. Just like that, okay? And so you may or may not see the water written in here, but it's because it's the same on both sides. If we include the water, then it'll probably say hydronium as a product here. But I just wanted to make it very obvious where that hydronium comes from. It's just that the hydrogen is donated by the nitric acid. So the fact that this is my hydrogen donor means that this is my acid. This nitric acid is an acid, and the water is acting like a base, which we'll get to in just a moment. So this is the acid, this is the base, and then we're making hydronium, and the nitrate ion is left over. Now you can see here, remember I told you that this will conduct electricity. Why? Well, because I have hydronium ion and I have nitrate ion, and for in the presence of ions, these will be what we call electrolytes. They conduct electricity. Are you okay?
Both the meeting IDs are not valid. So.
Oh, well, don't worry about it.
Okay.
So that's why strong acids are strong electrolytes. Okay, so essentially what's happening is I've got this nitric acid, and this hydrogen falls off of the molecule, okay? It dissociates, and it's a one-way reaction where the hydrogen and the nitrate are separate now. So a strong acid is like the hydrogen breaks up with the rest of the molecule, okay? It's like it never looks back. They break up and they don't look back at it and ever get back together, okay? That's a strong acid. So it's always a one-way arrow if there's a strong acid involved, okay? All right. In contrast, let's look at what a weak acid looks like, okay? A weak acid means the hydrogen comes off and then it comes back. So it's going to be a reversible reaction. So you can see here that with the weak acid, the hydrogen gets donated to the water and it forms hydronium ion and cyanide ion. But then it's reversible. In the reverse reaction, the hydrogen from the hydronium is donated back to the cyanide. Okay, and so if we look at which one's acting like an acid, acid is a hydrogen donor, right? So this is my acid, and then this guy is acting like an acid in the reverse reaction. Okay, and a base, we'll see in just a moment, accepts a hydrogen. So that means that this water is acting like a base in the forward direction. And the cyanide is acting like the base in the reverse reaction, okay? So the acid is the hydrogen donor, but the fact that the acid donates the hydrogen and then it comes back, right? It goes back and it's reversible. It's like they break up and then they get back together. They break up and then they get back together. In other words, if I were to draw it here, you would see that HCN, like the hydrogen breaks up from the molecule and then they get back together, break up and get back together. It's kind of like a high school relationship, right? You probably know couples like this at school, right? Where they break up and then the next day they see each other all cute and dressed up, and then one goes and apologizes and they get back together, and then they get into a big fight at lunchtime and they break up again, and then someone writes each other a note and they get back together, or a cute text or whatever. So you guys probably know high school relationships where people break up and get back together. I like to think of weak acids like high school relationships where they break up and then they get back together, break up and get back together. A strong acid would be like a divorce, like two people get divorced and then one person moves to France and they never see each other again, okay? The hydrogen breaks up with the rest of the molecule. That's like a strong acid, okay? Let's look at another example. Let's look at acetic acid, right? Only one hydrogen is acidic. Gosh, I wish I knew this yesterday, right? So again, whether something's acidic or not has to do, everything to do with the polarity of the bond. So once again, here's acetic acid, right? But only this hydrogen is considered acidic. So in other words, this hydrogen falls off of the molecule, which gives this oxygen a negative charge. And I've got now a hydrogen floating all by itself, right? Which can combine with water to form hydronium ion. But then also remember, opposites attract, right? So that positively charged hydrogen is going to be attracted to that negatively charged oxygen, and then they're going to get back together, right? And then they break up again, and then they get back together. They break up and they get back together. That's a weak acid, okay? So we could draw that out. 1, 2. Here's the way it would look. We would take CH3, COOH plus a water molecule, and it would be a reversible arrow. Oh gosh, I don't know how to do, oh wait, maybe I can. Look at this. It's almost like somebody was thinking about a chemist there. So reversible reaction, and then we'll get CH3COO minus acetate ion plus H3. Okay. So you can see that this one is acting like, oops, I didn't mean to do that. Okay, so this guy over here is acting like the acid because it's donating the hydrogen. The water is acting like a base because it's accepting a hydrogen. And then in the reverse reaction, the H3O plus is donating the hydrogen. So this guy is the acid in the reverse. And then this guy is the base in the reverse reaction. Okay, so once again, we can draw that too. You can see the hydrogen is coming from acetic acid and going to water in the forward direction, and it's going from hydronium back to acetate in the reverse reaction. Okay, so again, hydrogen donor is the acid. Okay, so and then you can always tell weak acid versus strong acid based on the arrows. If it's a strong acid, just one of the 7 strong acids, it's always going to be a one-way arrow, and if it's weak, it's going to be reversible. Okay, let's go on. Bases. Okay, a base, just like I've already mentioned to you, a base is a hydrogen acceptor. So if something is accepting hydrogen ions, it's a base. Bases also increase the concentration of hydroxide ions in solution. Which one is in solution? Okay. Those are 2 different definitions of a base. I guess I didn't say this for acids. I should probably go back and give you that definition of an acid too. Let me go back and do that to be thorough. An acid, I told you, is a hydrogen donor, but it's also something that increases the concentration of hydronium ions in aqueous solution. I'll go back and add that in. Sorry, I forgot when we were talking about it earlier. Okay, those are 2 different definitions of an acid. There's actually 3 in all, but I'm not going to teach you the 3rd one. You can wait till you get to college to learn that. So acid is a hydrogen donor that increases the concentration of hydronium ions in aqueous solution, and we saw why that happens. Okay. A base, back over here, bases are hydrogen acceptors that increases the concentration of hydroxide. Okay. All right, and then an alkaline solution is just describing one that has a base inside of it, so or within it. An alkaline solution has a pH that's greater than 7. Okay, it's a basic solution. Okay. All right, so strong base. A strong base is, they're strong electrolytes, okay, and the strong bases are very much like the strong acids where they're gonna have a one-way arrow. They'll be strong electrolytes also. They will conduct electricity. Okay, and you can see here that sodium hydroxide, I actually don't even need the water molecule here. Let me actually list the 7 strong or the 8 strong bases for you. Strong bases are, maybe you can write this in the margin or something. Gosh, I missed my classroom. Okay, strong bases. They're all the hydroxides of the alkali metals and alkali earth metals. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and then magnesium hydroxide, calcium hydroxide, barium hydroxide. Okay, so in other words, if you look at a periodic table, let me find a periodic table real quick. back to share screen. Okay, if you look at a periodic table, you see that all the alkali metals here, we don't even worry about francium because I should have chosen another color here. All right, here, all these alkali metals and alkaline earth metals. Okay, beryllium's generally left out, but lithium, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. I forgot to list strontium. Okay, the hydroxides of the group 1 and 2 metals, those are your strong bases. Okay, those are a little easier to remember. Okay, and just like strong acids, strong bases are strong electrolytes. They'll form ions in aqueous solution. You don't even need to worry about having water involved in the equation because they'll just break up and look, they form hydroxide. So remember, that was one of my definitions of a base, is something that produces hydroxide in aqueous solution. And there's your hydroxide. Pretty simple. You don't even need the water molecule. Okay, notice it's a one-way arrow. When it comes to a weak base, okay, ammonia, this is ammonia. Ammonia is very often representative of a weak base. We almost always see ammonia as the weak base. Just like with weak acids, weak bases have a reversible arrow. Okay, so it's a two-way arrow. Whoops, I actually shouldn't have drawn that yet. Hold on. I'm going to need the water molecule here. So let me add this in. I'm going to show you how this works. So I'm going to add in the water here because remember, all acid-base chemistry takes place in the presence of water. So this reaction is going to look like this. Here. I'm going to write it out for us first, and then I'll explain. Okay, so here's what this reversible reaction is going to look like when ammonia acts like a base in water. Okay, so what's happening here? Well, you can see that the hydrogen from the water is being donated to the ammonia molecule. So remember, the definition of a base is something that accepts hydrogen. So the ammonia is accepting a hydrogen. The water is donating a hydrogen. So that means in this case, water is acting like a base. I'm sorry, water is acting like an acid rather. Water is donating, so it's an acid. Ammonia is a base, so it's accepting, right? And then when ammonia accepts that base, we call it ammonium, right? This ammonium is one of your polyatomic ions that you should recognize, right? And then there's that hydroxide ion too. And I told you that's the definition of a base, is something that produces hydroxide ion in water. So there's the hydroxide ion. The hydroxide ion comes from the fact that water lost its hydrogen, right? And so the water is acting like the acid, ammonia is acting like the base, right? And then in the reverse reaction, you can see that the hydrogen is leaving ammonia and going to the hydroxide in the reverse reaction. So we can see that in the reverse reaction, ammonium is the acid and hydroxide is acting like the base, right? And so what we have here is something called conjugate acid-base pairs, in case you come across this. The ammonia, after it donates, oh, that's not what I wanted to do. There we go. This is good. This works. Okay. Ammonia, after it accepts the hydrogen, becomes ammonium, right? And so we call that a conjugate acid-base pair, in case you come across that term at any point. Conjugate acid / base pair. So after the base accepts the hydrogen, it turns into something that's an acid, right? And after this acid donates its hydrogen, it turns back into this base, right? So what we call them is conjugate acid-base pairs. For water, you can see that, we'll do that in another color. It starts as H2O, and then after it donates its hydrogen, it becomes hydroxide ion. And so after the water donates its hydrogen, becomes hydroxide, that's a conjugate acid-base pair right there. And then after the hydroxide accepts the hydrogen, it turns back into water. So we call that a conjugate. Okay. And so you might come across that. But again, weak bases are reversible, just like weak acids are reversible. Okay. Now, you may have noticed something, and that is when water can behave like an acid or a base, depending on what you put it with. Okay, so let's take a closer look at that. So, this word, amphoteric, describes something that can act as both an acid or a base, or either an acid or a base. Okay, and that prefix ampho or amphi means both. Okay, that means both. Right, like an amphibian lives in both land and water. An amphitheater is both covered and open air. An ambidextrous person is someone who can write with their left and right hand, or a switch hitter in baseball, right? So there's a good SAT prefix for you. Amphi or ambi means both, okay? And so this is something that can act as either an acid or a base. Water is a great example of an amphoteric compound. Water acting like an acid, well, I just showed you that. Actually, see ammonium, right? If you put water with a base, it'll act like an acid, right? So I'll show you NH3 plus H2O. Reversible reaction. Yields plus minus, right? Okay, so there's water acting like an acid. It's donating its hydrogen to ammonia. Water acting like a base, well, if you put water with an acid like HCl plus H2O, we end up with minus plus. Okay. So if you follow the hydrogen, this is what acid-base chemistry is all about, is follow the hydrogen. Here we can see the hydrogen is going from the water to the ammonia. Here the hydrogen is going from the hydrochloric acid to the water. So this is water acting like an acid because it's a hydrogen donor. This one's acting like a base because it's a hydrogen acceptor. So water can be an acid or a base depending on what you put it with. Okay, and that's what we call an amphoteric substance. Okay. All right, let's get into these pH and pOH calculations, and then we'll be out of here. This will probably take me about 15 more minutes, okay? So just a FYI, you guys can pace yourselves. All right, so when it comes to acids, this is just kind of a cheat sheet here. Acids have a pH, we already did this the other day, has a pH less than 7. Neutral compounds have a pH that's equal to 7. And bases have a pH that's greater than 7. pOH, and I'm going to explain this, what this means in just a moment, is the exact opposite. Okay, if I'm asking you about a pOH, acids have a pOH that's greater than 7. Neutral compounds have a pOH that's equal to 7, and bases have a pOH that's less than 7. And we're also going to be able to calculate these values of hydronium and hydroxide ion concentration. So for acids, you're going to have, acids create hydronium ions. So For acids, hydronium is going to be greater than hydroxide ion concentration. Okay. Let's see if I can cut and paste this to make it a little easier on myself. There we go. For neutral compounds, they're going to be equal to one another, and I really should put brackets around these, like nails on a chalkboard for a chemistry teacher not to write brackets. Equals. Let's try this. Get look a little bit better for you all. Screw this up. Let's try this. Okay. So for acids, hydronium ion concentration is going to be greater than hydroxide. For bases, they're going to be equal. I'm sorry, for neutral, they're going to be equal. And for bases, I bet you guessed it, you're going to see a hydroxide ion concentration that's greater than hydronium, like that. So they're opposites, okay? This is just going to be kind of a cheat way to make sure that you guys are getting the correct answers when you do your calculations. Okay, you can double check your work here. And then pH versus pOH, okay, for an acid, the pH is always going to be less than the pOH. I'll talk about what that means in just a moment. For neutral, they're going to be equal to each other, obviously, if they're both equal to 7. And the P is a lowercase p, by the way. And then bases, the pH is going to be greater than the pOH. Okay, so those are just kind of like cheat sheets to compare the values for an acidic versus neutral versus basic solution. All right, going on. Okay, these are some equations that you'll need to know. And I'm going to pause screen share for just a moment before I show you these couple calculations to show you a roadmap to using these calculations. Okay, so let's take a look at my whiteboard real quickly here. So essentially when it comes to acid-base calculations, there's 4 different things that you can calculate. You can calculate pH, you can calculate pOH, you can calculate hydronium ion concentration, or you can calculate hydroxide ion concentration, okay? Now, real quick, before I get into this, I want to talk to you about what pH, well, yeah, I want to talk to you about what pH literally means. Oh, you know what, let's do this, okay? pH literally means take the negative log of hydronium ion, okay? Now this P, this is actually something I didn't even learn until probably about 10 years ago. Not until I was teaching chemistry did I learn this. That P actually means take the negative log of, okay? So in other words, when you guys see in your mathematics or any equations, if you see that, you know to add. If you see this, you know to subtract. If you see this, you know to multiply. If you don't see this, you know to divide, right? Well, if you see the prefix P, or the P is a mathematical operation that means take the negative log of. So pH is negative log of H. pOH is take the negative log of OH concentration. Okay, it just means take the negative log of. I could have P8 would mean take the negative log of 8. I could have P Elisa, take the negative log of Elisa, right? P just means take the negative log of, okay? And so don't let it scare you. It looks a little scary, but it's not bad. And I don't know if you guys have reached logs in mathematics yet, but hopefully you have. Hopefully that's not unusual. That's just a button on your calculator that says log, and you hit it, okay? So these are the 4 values you could know about an acid-base solution. pH, pOH, hydronium ion concentration, and hydroxide ion concentration, okay? Those are your 4 different values that you should be able to calculate for acid-base solutions, okay? Now, at 25 degrees Celsius, and we're gonna assume that all of these are at 25 degrees Celsius, okay? All right. If I give you one of these values, you should be able to find all the other three, okay? So if I give you pH and I ask you for POH or vice versa, then you're going to use this equation. pH plus POH is always equal to 14, okay? If I give you the hydronium ion concentration and ask you for hydroxide ion concentration or vice versa, then you're going to use the fact that hydronium ion concentration times hydroxide ion concentration is equal to 1 times 10 to the negative 14. Okay, in other words, pH is always on a logarithmic scale. So is the Richter scale for earthquakes. Okay, they're all based on factors of 10. Okay. If I give you pH and I ask you for hydronium ion concentration, you're going to know that the pH is equal to the negative log of hydronium. And that's if I give you hydronium and I ask you for pH. If I do the opposite, where I give you pH and I ask you for hydronium going this direction, then you can use this equation. It's the inverse of this equation is that the hydronium ion concentration is equal to 10 to the negative pH. That's just, these two are inverses of one another. It's just that if I give you the pH, it's a little hard to solve for hydronium ion concentration. All you have to do is just do 10 to the negative pH will give you hydronium ion concentration. Okay. And likewise, for going from OH to POH, you can use the fact that POH is equal to the negative log of hydroxide ion concentration. But if I asked you to go the other direction, where I said, what's the hydroxide ion concentration given the POH, you would use the inverse of this, but the inverse of that is just the same. OH concentration is 10 to the negative POH, okay? And so really those are just inverses of each other, okay? So there's basically your roadmap to pH calculations. If I give you one of these, you just use the equations to find the other three. And most of you are pretty good with mathematical skills, so I would venture to guess you're going to be pretty good at this. But just know that this is only true at 25 degrees Celsius, okay? If you change the temperature, you can change the pH of a substance. Most of the time we're going to be at 25 degrees Celsius, so nothing to worry about there. Okay, let's do a couple of examples, and there you see the 4 equations, right? Pretty straightforward, okay? Let me show you how they work, okay? So first example, a solution has a hydronium ion concentration of 1 times 10, this should be to the negative 7 as an exponent. Calculate the pH, okay? So I've given you hydronium, and I'm asking you for pH. So I'm gonna use the fact that pH, here we go. The pH is going to be equal to the negative log of my hydronium ion concentration, 1 times 10 to the negative 7th. Like that. So you just take your calculator, okay? Everyone get your calculator if you don't have it. Okay, turn it on, and just all you have to do is hit negative. Make sure you're not hitting the minus sign. You're not subtracting, it's the negative, and then there's a log button right there, log. Just find the log button. Negative log of 1 EE negative 7, 1 times 10 to the negative 7, and you get 7. So here pH is equal to 7. In other words, that describes a neutral solution. All right, next one. A solution of hydrobromic acid has a pH equal to 4. Is this solution acidic or alkaline? Okay, well, remember, anything with a pH less than 7 is an acid. So it's an acid, it's acidic. Determine the hydronium ion concentration. Okay, so now I've given you the pH, but I'm asking you for hydronium ion concentration. So it's gonna be easier for me to use this inverse equation, okay, where I can say, well, the hydronium ion concentration is going to equal 10 to the negative pH, which is 4, right? 10 to the negative 4. But you're not going to leave it like that. You want to put it in proper scientific notation. So I can just say that this hydronium ion concentration is equal to 1 times 10 to the negative 4. And then it's a concentration. So what are the units? It should be molar, moles per liter. There are no units on pH, but there are units on concentration. Don't forget, you guys have already learned that. Okay, so that's your answer right there. Okay, and then this was my answer up here. I guess I should put a circle around it. Okay, and then next it says, what is the pOH of the solution? Well, we know I've given the pH. I can find the pOH quite easily. pH plus pOH is equal to 14. So I can say, well, all right, 4 plus the pOH is going to equal 14. Okay, and so therefore pOH must equal 10. Okay, so that's pretty straightforward too, pretty simple. Right, so there's my answer. It's an easy subtraction. Okay, and that makes sense because if you look back at the cheap little table we filled out on the previous page, you would expect that an acidic solution has a pH that's less than 7, but a pOH that's greater than 7. Okay, all right, let's try one more. Last one. Thanks for your patience, everyone. This is tough chemistry, especially to teach through a screen. Okay, you have a 1 times 10 to the negative 2 molar NaOH. Okay, NaOH is sodium hydroxide, and then it asks, is sodium hydroxide an acid or a base? Okay, well, you guys should know that sodium hydroxide is, if it has hydroxide, it's a base, okay, and this is a strong base. How do you know? Because there's hydroxide. Present. And if there's a hydroxide present, it's a base, okay, because bases always produce hydroxides in aqueous solution. Okay, write the equation for the dissociation of sodium hydroxide in water. Okay, well, all that happens is that sodium hydroxide, you don't even need to include the water. If you want to make it aqueous, you can, that's fine. So we can prove that it's in water, but essentially what happens is that the sodium ion breaks up and the OH ion break apart. And that's what it would look like, okay? And it's a one-way arrow because sodium hydroxide is strong, right? And then it says, what is the hydroxide ion concentration in this solution? Okay, well, if you think about this in terms of stoichiometry, right? 1 times 10 to the negative 2 molar means that I have 1 time, this is gonna be so much easier if I do it on my board here. Well, let's see if I can do it here. Okay, 1 times 10 to the negative 2 moles of sodium hydroxide, and that is per liter of solution, right? So let's see if I can pull this off here. Per liter of solution. That's what molarity means, right? So now if I can just think of this in terms of stoichiometry, I have a 1 to 1 to 1 ratio here. So I can say times, I'll put the mole ratio in. There's 1 mole of hydroxide ions produced for every 1 mole of sodium hydroxide. That's just based on the balance equation. And so that, then I can see that moles of sodium hydroxide will cancel, right? And I end up with my answer, which is 1 times 10 to the negative 2 moles of hydroxide per liter, which basically means molar, right? And that's my hydroxide ion concentration. Okay, 1 times 10 to the negative 2 molar is my hydroxide ion concentration, moles per liter. Okay, there you have it. All right, next it says calculate the hydronium ion concentration. Well, if I have hydroxide ion concentration, can you just use my little map to figure out hydronium ion concentration? So I know that the hydronium ion concentration, H3O plus, times the hydroxide ion concentration, which I just solved for, 1 times 10 to the negative 2, equals 1 times 10 to the negative 14th. Oops, 1 times 10 to the negative 14th. So all you have to do is plug and chug into your calculator. Don't forget to put parentheses around anytime you have scientific notation in the denominator. So I'm going to do 1 times 10 to the negative 14th, or 1 EE negative 14, divided by parentheses 1 EE negative 2, close parentheses, and I get a hydronium ion concentration, H3O plus. This is a concentration, so I should put brackets around it. Equals 1 times 10 to the negative 12th. Units are molar because it's a concentration, right? And then it says calculate the pH and the pOH of the solution. Okay, well, the pH is simply going to be the negative log of the hydronium ion concentration, which is 1 times 10 to the negative 12th. And then my pOH will simply be the negative log, because that's what P means, negative log of 1 times 10 to the power of negative 2. Okay. So when you solve for that, you should find that the pH is equal to 12. Plug and chug into your calculator. Just use the log button. pOH is equal to 2. So sure enough, pH plus pOH is still 14, right? And then you just ask yourself, does this describe a basic solution? A pH of 12 and a pOH of 2? If you go back and look at your little cheat chart, it does, and we're describing a base. So good, that means our calculations are correct, okay? So that's it. That's how you do acid-base calculations. It's a pretty simple little roadmap. So at this point, you should be able to go back to our classroom here. And this is what I'd like you to try this weekend, are these acid-base calculations. Oh, that's the answer key. Let me look back at the other one. Okay, so here's what you get. The back is really just for you to do calculations to show your work. Really all you need to do is fill in this chart here. And you'll notice I give you the formula for something. I ask you for the name of it. You tell me if it's a weak or strong, acid or base. And then I give you one of these 4 values. In this case, I gave you hydroxide ion concentration, and you have to solve for the other 3. Okay, and the way you do that, whether you go, wherever you go on this map, it doesn't matter. As long as you start, you can go in either direction to solve the others, okay? So there's only 6 problems here, but they're good practice for you to know how to do pH and pOH calculations. And this is the kind of stuff you'll see on your test on Monday. So I might ask you, or your quizam, I should say, I might ask you, is this strong or weak? I might give you one of these 4 values and ask you for one of the other 3. I might ask you about neutralization, predict the products, reaction of acid plus base makes salt plus water, or I might ask you about the reaction of an acid with an active metal. Okay, these are all anything that I talked about on Wednesday or today is fair game for the quizam. And I know I didn't show you guys any explainer videos in this unit. If you want to watch explainer videos, they're definitely out there. You can go to bozemanscience.com and watch them, or you know, anything that you can find on YouTube. There's probably even some from my past students on YouTube that might be helpful for you on my YouTube channel. Okay, so I'm going to stop there for today, and I wish you guys a wonderful weekend. Quizam on Monday, and then we're going to see you on Tuesday. We're going to actually turn on our cameras and see each other's faces and hopefully smiles as well. So have a great weekend. Thank you for coming and for your patience. If you have questions, bye.